especially Dimitris, who makes the meeting very hospitable. Crete is an amazing place. It's the source of mythology, Greek mythology. Zeus is from here, Minotaurus, and I'm sure it had a big part on the Trojan War, beautiful Helen and so on. And all these things, they weren't just out there, they were just extensions of the humans to the next possible level, as mythological creatures. So the humans were great, and still are. They wrote big parts of history, so I'm really happy to be here. Personally, I come from Rhodes, another island, has its own history, and you might be familiar with Colossus of Rhodes, a huge statue stood at the front of the harbor, and so big that boats would pass under its legs, and as you see here, it was made out of copper. The area is seismogenic, there are many earthquakes, probably fall down, and it was, of course, used, melted again, and used to make weapons. You know, copper was like gold, very precious. So, we don't have any evidence of it. It reminds me of the story of Majorana fermions that I want to talk to you about. We believe they exist. There are, like Colossus, there are historical evidences that we crossed references, but we really want to touch it in order to say, yes, that's it, right? It's really, but we are very close with Majorana fermions, and hopefully we'll say that with certainty. It's a big effort, experimental effort, to discover Majorana fermions. I will describe you what they are, as well as alternative interpretations of Majorana fermions that could help you to simulate them in the laboratory or theoretically to create proposals. In the laboratory, when we do simulations, we are more comfortable with spins, not fermions, and certainly not Majorana fermions. So I will use spins as my weapon of choice and try to formulate everything in terms of spins. In doing so, I will make the concept of Majorana fermions more tangible, but also some fundamental characteristics of Majorana fermions will be transformed. So we have to be careful to see what we're gaining and what we're losing, or how things actually become. The systems I will look into are in a general class of topological phases. So there are topological superconductors. They have very similar properties or equivalent properties to topological insulators. But I will restrict exclusively to one dimension for I understand that. Then we will move to higher, one can move to higher dimensions. So I will mainly be talking about spin-half particles. But superconducting systems are very interesting. So we would like to get there where Majorana fermions exist. First of all, they give rise to very interesting physics. Indeed, if we have Majorana fermions, moving a lot, right? If we have Majorana fermions, giving a hard time to the camera, then these are new types of particles, and we really would like to get our hands on and see how they behave, study their properties, and establish them, put them in the elementary particle periodic table. But also, we can use them to encode quantum information in a fault-tolerant way. Now, you might not be a big fan of quantum computers, we don't blame you. You might just be a recent believer with the 1 billion from the European Union. But even if you want to be pure physicist, being able to encode information or states in a fault-tolerant way means that you can create quantum phases that are also fault-tolerant. Okay? Robust phases of matter that are not destroyed easily against perturbations or temperatures. So that's interesting for both pure physics, fundamental physics, as well as possible applications to quantum computation. Also, in my presentation, I'll be going rather slowly, so do ask me questions. I will first look at systems of one side, and then I will look at two sides, and then we go to infinity from there, obviously. Physicists do. And I'll be very careful to explain what a quantum simulation is, what you gain and what you lose. And do please ask me questions. Let's clarify some issues like that. So let's build the culture to understand. Because topological effects are funny, they're non-local. And when you start making transformations, some of the properties change. So what we would like to observe, what is important. So, let me just start with spins. These are spin half particles or states. It's exactly what a qubit is. You have two states, 0 and 1. This is a Hilbert space. And this is the weapon of choice of experimentalists. Two states, let's isolate the rest and work with them. And for photons or atoms and so on, this is an easily recognizable Hilbert space. We use the Pauli matrices to transform between them, and we define, as the previous lecture happened, also the ladder operators, the sigma plus and the sigma minus. So we'll be using these tools. Also, the sum of them gives you the sigma x. A typical Hamiltonian is just a sigma z. You turn it on with some magnetic bead, and you create two levels now, ground state and an excited state, spin up and spin down, with a separate energy, and you can prepare your state to be in the ground state. Having a large energy gap helps you to protect this state against perturbations. So, environment that usually acts locally, that means it likes to act on one side exclusively. We'll try to change the population from the ground state to the excited one. Okay. And if the energy gap is large, then the environment needs to put a lot of energy in order to do that. And if it acts perturbatively, it will have a weak effect on doing that. Okay. So, by creating large gaps, we protect the ground state encoding. And this is really how we use in atomic physics when we compare ground states that are really, really stable, ion traps and so on, cold atoms. So it's very well protected. Now, another concept which is important is how the environment acts. First of all, it can do two things. It can add perturbations to a Hamiltonian. So this is a coherent type of error. So you add to the Hamiltonian an extra term that you didn't think it was there. You didn't know it was there. Or it can act probabilistically, like what temperature does, and it tells you with a certain probability, for sure an error will happen. There's not a perturbation, it's a classical thing. Okay? So it's very hard to protect against temperature. And topological systems promise to protect, we will see, we will show, we will demonstrate they can protect against perturbations. Going the extra step to protect against temperature is extremely hard because the errors will happen. You have to create almost a classical macroscopic effect in order to protect against that. This will not be the topic of my talk. I'll talk mainly about protecting against perturbations, but I'll be motivated in terms of protecting against temperature, against probabilistic errors. And the way I will do that, so that will be my first component, I will deviate from a single particle into many particles and encode my information in many states, so that when the environment acts on individual sites, if my qubit is not really encoded, qubit states are encoded on one state but on many different sites, then errors will happen probabilistic on individual sites, and I'm hoping that on average I'll be able to retrieve the initial information. That's the spirit of classical error correction. Just encode, copy the information many times on many bits, and then errors happen, but then you vote, see majority, and then you correct your errors. So you can tolerate a big amount of errors like that. So quantum error correction works in a similar way. You don't copy the information, but you encode it on many subsystems, so that when errors happen, you can still retrieve it. You can tolerate a certain amount of errors. So that's what I'll be using. And actually, this concept of quantum error correction, you can use it to protect quantum phases as well. And that's part also of this talk. So I will deviate from a single site that for sure a single error can destroy it to many sites where my encoded information can be protected against probabilistic errors. Okay? But I will not deal with this protection in this talk. It's just a motivation to tell you why I'm going from a single site to many. Let's now move to another system, the fermionic systems. It's the concept of a mode. I have a fermionic mode, and now this mode can be populated or empty. I put it here as a little circle. Now if it's empty or populated, and then we use creation and annihilation operators in order to transform from one state, the 0 is the empty, the 1 is the populated, the creation operator is from 0 to 1, the annihilation from 1 to 0, and also if you act on one, you try to put another fermion on the same mode, but it's already populated, it will tell you I don't want to do that. This is the Pauli exclusion principle. That's like to have two identical fermions on the same side. So, and this is the ideal qubit, right? Imagine a qubit that stays only between 0 and 1 and doesn't mix with the rest. It's a beautiful, nice qubit. Also, we have a population operator, A dagger A, acting on 0 gives you eigenvalue 0, or when it acts on 1, it tells you I have one population there. So we can measure the population of a mode with this operator. The strange property of fermions that people don't like to use them very much. Certainly, I as a student, I felt uncomfortable getting into fermions, is their anti-commutation relations. So A with A dagger plus A dagger with A is 1, A with A anti-commutation with a plus sign is 0. That means that A squared is 0. In other words, you can't take two fermions out of one mode, or you can put two fermions in one mode with the other operator. But even more intriguing is that if you have two modes, two fermionic modes, the corresponding fermionic operators anti-commute. And this is really strange. This is really very unlike bosonic or spin, let's say spin and borders, like qubit states, local to Hilbert, two-dimensional Hilbert spaces. If you change them, they commute a tensor product structure, but fermionic tensor product structure, it needs an anti-commutation relation. Okay? And this is very fundamental for the fermions. And this gives rise to the fermionic statistics in -1 sign that we had before. Hamiltonian I can introduce for a single fermion. It's just a chemical potential. I can use a population operator that will increase the energy if the mode is populated, or it will decrease it if it's empty. So here I have again the same picture as before, all these normalizations I have here, just to make it symmetric around 0. I can have empty mode with energy minus mu to a populated mode with energy mu. Again, the same type of error is going to happen. But here, if I have an isolated single fermionic mode, it's not possible to change from full to empty if it's isolated from the environment, because that will correspond to creation of a fermion, and conservation of number of particles would forbid that. But of course, a fermion can come from outside and populate one mode. Okay, so this is an extra type of protection the fermionic systems have. Again, the same story can happen here. I'm expecting that local perturbations, so local probabilistic errors, will happen. So from the environment will happen locally. And it will happen in the form of chemical potentials. Okay? Even if I look at the big systems, that's the time of errors that there. So for the spin systems, it was local zero fields. For the fermionic systems, are chemical potentials. Let me take now another step, maybe something that's not so familiar, or maybe it's very familiar by now. It's a mathematical decomposition that we've been doing already when we've been solving the Ising model and so on, but we haven't given it the proper name, the Majorana name. So let's pick up the fermionic mode, the single fermionic mode, and decompose it, especially its creation and annihilation operators, into two parts. A real part given by A plus A dagger over 2, and its imaginary part, A minus A dagger over 2. So I get two operators out of it, okay. Gamma 1 and gamma 2, that they have interesting properties. Up to now, it's really a mathematical step. I do take a single mode and I write it as two other operators that really correspond to the same point where this mode exists. It's just mathematics anyway. An interesting property of these new operators, gamma 1 and gamma 2, is that their complex conjugate is, the Hermitian conjugate is equal to themselves. So the particle and the antiparticle are identical. That's very similar to the yin and yang, good and bad being together, right? The annihilation operator and the creation operator are the same thing. Also, it's interesting to see how the local Hamiltonian chemical potential is translated in the language of Majorana fermions. If you, so you can reverse this transformation from gamma 1 to gamma 2 to A and B, A and A dagger. So A is equal to gamma 1 plus I gamma 2. You can substitute it in here. Hermitian conjugate, and you'll find that it's actually equal to gamma 1 times gamma 2 with an I factor, because, so that it's Hermitian, and the coupling is that. So it looks like a tunneling term of Majorana fermions. So I call these Majoranas, okay? So it's like a tunnel term from gamma 1 to the gamma 2. But of course, it's very hard to make sense out of these modes, these Majorana modes, because you can't make sense of the local Hilbert space for Majorana modes. You can't write a Hilbert space for gamma 1 and a Hilbert space for gamma 2 and then join them and get a Hilbert space of a fermion. But it's alright. I don't care about that. I can say I have gamma 1 and gamma 2, but the Hilbert space is really the Hilbert space of the fermionic mode they came from. So a pair of Majoranas, I can join them together and then talk about their the Hilbert space. Okay? I can actually pick up any two Majoranas and create the Hilbert space out of them. But I cannot talk about the Hilbert space of an individual Majorana. So people say that if there is a Majorana somewhere, there's another one somewhere else. Go and find it, and then build your Hilbert space. So you don't need to worry about an individual one. though it's an interesting question, and some theoretical physicists trying to address that, Roman giant and so on. Okay, let's move to two sides. Okay, as a promise. Let's build a superconducting Hamiltonian that has a tunneling term here. Basically, it takes, so I have emphasized the creation and annihilation operator for side A1 from the second side is A2. A tunneling term takes a population from here to there if it's empty, and the other way around, for missing conjugation. And I have this pairing term, the second term. What it does is something very funny. It picks two fermions. If two modes are populated with fermions, it picks them and puts them to the vacuum. And if these two modes are empty, out of nothing it creates a pair of fermions and populates them. Okay? So, and this is a very funny Hamiltonian. Now, in order to make sense of it, because you know, there's a conservation somewhere out there about fermions, right? What happens? Well, out of these two fermions, you can create a Cooper pair. Okay? And then you can condense these Cooper pairs. You can create a molecule of two fermions and then condense them.
Excuse me, may I ask just a question to understand? Now you have indexes in Fermi operator 1 and 2. Before you don't have, you didn't have indexes. So how, what's happened? Why now you have indexes before you didn't have?
Yes. So before I had only one site, so I didn't use an index. I had only one single mode. Now I have two modes, and I name them 1 and 2, and then I give the corresponding creation and annihilation operators.
Okay.
So I moved to the two-side problem, and in a couple of slides I moved to the infinite-side problem. I'll index them as 1, 2, 3 up to infinity or n.
So distinctive fermions with 1 and 2 to different fermions.
Because of big room and we can't hear the questions in the back, there are microphones around, or...
Well, I repeat the question. So the question is, why what do the indices do here? And I presume you don't feel comfortable because they don't have a spin, and how do I create Cooper pairs out of without having spin particles and so on? Is that the question?
Yes.
So indeed, the index 1 and 2 is an index of position.
Okay.
So I can distinguish them. Also, there could be different species as well, and then different species could create condensates and so on. Could be in the same position. Could have a spin. So as long as I can distinguish them, then I can create different things out of them. But I won't go into the how I do it. I can write this pairing term down, and it could be coming out of a molecular state of two fermions. So indeed, there could be a molecule, and then these molecules, it's a quantum state, but I can condense them. Okay, and then I could have the bosons. I can condense them. There are two fermions together, give you a boson. I can condense it. They disappear out of the quantum Hamiltonian, and they just determine the coupling here in front of the pairing term. So I lose the conservation of particles with this pairing term, but I still have the parity. So if two fermions disappear, they disappear in pairs, or if they create pairs. So if I start with an even number of fermions, I'll remain in the even subsector of number of particles. If I start from the odd number of fermions, I'll be always in the norm. So this Hamiltonian won't change that problem. What we will do now, we will treat this Hamiltonian in two different ways. First, we will try to transform it into a spin language, and second, and see how it becomes. And second, we'll transform it into Majorana language. Transforming it into the spin language will help us to make it look like things we're familiar, like spin half Hamiltonians and operators and states. Our qubits are well beloved cube. I will transform it also in the language of Majorana fermions in order to see if if we gain anything, actually, this last step is what we do in order to solve analytically this Hamiltonian. And I would like to make transformations because you have to admit this is a hard Hamiltonian to deal with analytically and experimentally. I would like to do something else about it. I would like to massage it a bit. The way how to move to the spin language is to use the Jordan-Wigner transformation. Now these transformations take you from fermionic operators, the creation equation for each side I, to a spin operators. So basically A corresponds to sigma plus and A dagger corresponds to sigma minus. They have one at the off diagonal element here or one at the other off diagonal element, zeros everywhere else. And these operators for a single side behave exactly as we wanted. If they anti-commute and if you square them, they give you 0. So they have all the properties of single fermionic mode. But if you have more sides, many sides, then you need to add this tail. It's a non-local tail. So we're talking about an operator that's on I. Now you write as an operator that's on side I, but it has a tail of sigma z value operators acting on all the previous sides. There's a huge non-local operator. There's an operator which is a beast, boom, like a block, acting on anything up to the side you want. It's easy to write them for two sides. You have A1 is just sigma 1 plus, and A2 is sigma 2 plus, and I have to use the sigma 1 z acting here. So A to Y is a local operator here. In terms of spins, it extends to two sides. And my system is two sides. If I have n sides, then my operators would just expand, extend in the same way. Please.
So firstly, before transformation, two ways, ordering sides from left, right, from right to left. How much communication is first, or just two different ways to do that?
Very good. That is the equivalent, but you have to make sure that whatever convention you use, you have to stick with it. All your other calculations have to stick with that. So if I start from left to right, everything has to happen in that way. I could do exactly the same thing with the other notation. So let's see how our Hamiltonian, our two-side Hamiltonian here, the superconducting Hamiltonian, how does it behave when we make this transformation? So we start with superconducting Hamiltonian. There's all these pairing terms. Now A1 dagger is sigma minus, A2 is sigma z, sigma plus. So I put the indices here, and then the pairing terms is minus minus on both of them. I can make the product, so I can write them explicitly better. I have this operator plus this operator. Then, what did I do here? Okay, yes, I'm pulling out sigma 1 minus sigma 1 z from both terms. Here it is, sigma 1 minus sigma 1 z. And then I put in the parentheses sigma 2 plus plus sigma 2 minus. And this gives me sigma x at the side 2. I have this one. Now this one actually gives me sigma minus. Okay, the product of these two gives you again the same thing. Now I take the Hermitian conjugate. It doesn't change this matrix because it's already Hermitian, but what it will do is to make this Hermitian matrix by adding the 0, 1, 0, 0 matrix to this one. So basically again you have 1, 1 and 1, 1 on both sides, 1 and 2. So basically you get the sigma x, sigma x. Okay. The Ising interaction was earlier on. So the superconducting, all these terms here, they look really funny. Under this transformation gives you the Ising Hamiltonian. You're right. It's a huge simplification. Ising is very common. Two spins, you can always work around and create this interaction. So it's equivalent to our superconducting Hamiltonian that promises to give rise to Majorana's, as we will see in a minute. Let's see what this Ising interaction, what does it do? Well, first of all, the matrices are written in the X basis, so the eigenstates of Pauli matrices, the X Pauli matrices are the superposition of the up and down with a plus sign and with a minus sign. So when I write the eigenstates of this Hamiltonian, I will have a double degeneracy. So both for the ground state and the excited. The ground state with plus will give me a plus on both on the action of both Paulis here. With the minus sign, they have the lowest energy. If both are in the minus state, then I'll get two minus signs. The product of them is again plus. Excellent. I get again a lowest energy here. I normalize it happening just to keep it simple. The excited state is if I have one plus or one minus, I get the minus sign out of the action of sigma 1, sigma 2, and with the minus I go on. I have two states of those. Now, I will go and encode the qubit on the degenerate ground state. Okay? So, for a qubit, I need superposition of a 0 and a 1. The logical 0, I'll use one of the ground states. The logical 1, I'll use the other ground state. And I want to encode it on ground states that I have the same energy, otherwise, so that I don't get any dynamical phases accumulating while time passes. So if the two states have exactly the same energy, then my superposition will not decohere, will not dephase. Okay, and that's what I want to achieve. I don't like dephasing, so I like the degeneracies. And also, we want to go from one spin to many spins, or many signs, because to avoid the problem of probabilistic errors, I'm encoding things in microscopic states of large scale. So, we did it for 1, we did it for 2. Easily you can write down the Hamiltonian, superconducting Hamiltonian from many sides, and there's many sides here. And it's basically, I'll index it with I and I plus 1, and a sum of all of i's. I use a finite chain from 1 to n sides. And if you do exactly the transformations we saw before, you see that we get the Ising Hamiltonian, the XX, or nearest neighbor pairs. And that's really strange, all right? That's not a trivial statement, because I did use non-local operators to go from one to the other. I've used, for example, if I wanted to treat the superconducting interaction between these two, I was substituting the operator here with the spin operator that was huge, included all the signs here. And then I transformed the fermionic operator here with a spin operator that acted, boom, like a block of concrete, every other spin. But so it happened that these tails, so I had the product of these two, so when I made the product of these big blocks, these tails squared to 1 and disappeared. Okay? And I started from a local Hamiltonian, nearest neighbor Hamiltonian, and I went to another local Hamiltonian, only nearest neighbor. Okay? Sort of a miracle. Okay? You do a non-local transformation to a local thing, you get a local thing. And it's very rare to have. The ground state of the spin Hamiltonian, again, is the same thing. They're pairwise, they have all to be the same. So if these two are the same, the two neighbors have to stay the same, and so on. So you are full of plus states, or all of them are minus states. These two states are degenerate, exactly. And I can use them to encode my information. My qubit is still one qubit. But I want it to be well protected. And that's what we're doing. I'll be using pluses and minuses for the logical 0 and logical 1. Now, while this protects against some probabilistic errors, like folding and so on, you can get around them, it doesn't protect against perturbations of the form of sigma x. So if I turn on the dualist small Hamiltonian, so I have these rising there, then I add a small Hamiltonian, a straight magnetic field down there, I add it to my system, then it will cause a phase factor to accumulate between the pluses and the minuses. So a simple local, okay, acts only on one side. If I put it on side I, local sigma x will actually distinguish between the plus and the minus state, the local plus and minus states, because the plus and minus are eigenstates of sigma x with different eigenvalues, as we said earlier on. Okay, so they will have a relative phase factor accumulating. So it will distinguish between the two. So it will destroy your cube by sigma z and sigma x will do it. Sigma x is the bad guy. Okay? Sigma z will try to lift the energy of those, but if you have a large energy gap, it will be eliminated a little bit. Any questions up to now? We're moving slowly, but I'll be very happy to take any questions. Let's move to Majorana fermions. Okay. Let's now write exactly the same superconducting Hamiltonian in another language, the language of fancy physics. Okay, fancy physics. And try to get some physics out of it. So the superconducting Hamiltonian I assign to the two modes A1 and A2. For Majorana, so A1 will have Majorana gamma 1 and gamma 2, so A1 will be gamma 1 plus I gamma 2. A2 will be gamma 3 plus I gamma 4, so I'm doubling the modes, the Majorana modes. And then I write A1 dagger gamma 1 minus I gamma 2, A2 gamma 3 plus I gamma 4. Take also the superconducting, the pairing term of minus signs, and add a Hermitian conjugate, and you just do the calculation, and then you find that this whole big beast over there is just gamma 2 times gamma 3 with an I factor. So it simplifies dramatically when you write it in terms of Majoranas, and that's actually what you do when you're solving the Ising model. You actually bring it in this form without knowing it. The Ising model, you make the derivative transformation, you make it fermions, you make Majorana, and then you make a rotation, poof, you find the spectrum. But you don't talk about it, right? Now we'll talk about it. And indeed, gamma 2, gamma 3, which is the full interaction between the two modes, becomes an interaction between only two Majoranas. Gamma 2 and the gamma 3, and the gamma 1 and gamma 4 just don't participate in the Hamiltonian. So I will recombine my Majorana fermions in a different way. Because I can do it, I just need two of them in order to create a fermionic mode. It doesn't matter which two, it's just a language for mathematics. So now I'm using mathematics that are convenient for me. I'll combine gamma 2 and gamma 3 together into the mode B1, so that this gamma 2 gamma 3 will become just the chemical potential on a fermionic mode made out of gamma 2 gamma 3. So before we started with a chemical potential, and then we saw that it's equal to the tunneling term between its corresponding Majoranas. Now we went the other way around. We had two Majoranas with the tunneling term. We create a single fermionic mode. It's an imaginary fermionic mode. It lives in our head or in our paper, right? We started with this fermion, but I can write it down, and my Hamiltonian becomes just a single local. Basically, I diagonalize the problem. Okay, that's the mode. It can be populated, and then we can write the eigenvalues. Okay, that's what we do on that stage, and that's really why this solves the Ising Hamiltonian. But on the side, there is this B mode that is made out of the edge Majoranas. can still combine them mathematically, and I can create, I can populate this mode, or I can keep it empty, whatever I like. And it will create a degeneracy in my system. That's like plus another mode with B dagger B with zero energy at the front, zero eigenvalue. Okay? So if I haven't populated the empty, it won't change the energy of the system. So you give you degeneracy, double degeneracy of all the states of your system. And this is very interesting. And now there's something else. Before I told you that Majoranas are just a mathematical construction, I just made them in order to calculate the real and imaginary part of fermionic operators. Now, they don't live necessarily on the same side. They're not constructions on the same mode, fermionic mode. They're constructions that have been delocalized and move on different sides, independent. So they become physical. Okay? I'm not talking about mathematical construction anymore. I'm talking about a physical object that is localized on edges of my chain. And this is a fundamental step. The same thing as we went from superconducting chain to the Eisen chain, we can do now from a superconducting chain to a Majorana chain. Indeed, for n fermions, for each one I can have a pair of Majoranas and combine together in order to give me the previous modes. But the Hamiltonian here will just introduce each term of the interactions, both tunneling and pairing, will give me these little tunnelings between neighboring Majoranas. But it will exclude, so which are written here, but it will exclude the endpoints. The endpoints won't be part of your Hamiltonian. No matter the size of your chain, the end Majoranas will be sitting there decoupled and create a fermionic mode out of them and have it populated around. It can be as far away as I want. The other interesting thing is that these modes, of course, it's a fermionic system. I have to populate the valence band, and then I decide to populate in order to get the ground state, and then I decide to populate the zero mode or not. But you can do either thing. You get a degenerate state, right? At zero energy, just as right at zero. Now I can use this degeneracy of the ground state in order to encode my logical qubit. Two states I mean. Either having this B dagger B, the fermionic mode of the two-edged Majoranas, either being populated for the zero logical, or being empty, or being full for the logical one. Okay, and this is quite interesting. Errors happen locally, but they will not affect my Majorana modes because they are encoded non-locally on both qubits. I can act actually with chemical potentials on the edge modes, but they won't change the zero and the ones. They will come what local chemical potentials everywhere will do is will change the localization of the Majorana modes from being completely on one side to actually being extended exponentially with exponential tails in the inside of my chain. Indeed, a chemical potential, what it does, it creates a little link between these two sides. So for small chemical potentials, we'll have an exponential tails of these modes getting into the bottom. But the overlap between this mode and that mode will be exponentially small as a function of the length of your chain. Please. You have it. It leaves the degeneracy, indeed. So now, the question is, what is the strength of the amplitude of this energy lift. And as these tails are exponentially small, this lift degeneracy will be exponentially small as a function of the size of your chain. So anything that is controlled exponentially, experimentally, is very good. You have a very strong knob to turn things on and off if they have an exponential dependence. So I can make my chain large enough and suppress this lift of degeneracy efficiently. So a local chemical potential acting on size, or any size, or all size even, will have an exponentially small change in the energy. So I can suppress and make these states degenerate and avoid defacing. Please.
So I was actually a bit confused with the spin analogy that you made. Because if I write it in spin, I have to use the Jordan-Bigger transformation, right? So any local operator in the spin language will become T-local. And
Exactly, yes.
It won't work in the spin language.
We're
So
talking
I
about, absolutely, that's the whole point I want to make. I'll celebrate that. I'll make a little dance about exactly this point. But it will be my dance, not yours, right? So the point was that, the question was that, we made the Jordan-Bigger transformation, all right? Local errors in the spin language will become non-local errors in the other language. But these are two different systems. Here I'm looking at a fermionic system. It's made out of fermions, and the errors will be, the environment will be acting locally to my fermions. That will be a chemical potential. That's what we can do. And I'll be exponentially suppressing that. And soon, I'll be comparing the two. So even in the spin language, I looked only at local errors. Because that's what the environment does, acts locally. I took this assumption at the very beginning. I need only Zeeman fields. So, let's compare the two. Indeed, it's exactly the point raised a minute ago. The Jordan-Wigner transformation is a non-local transformation. It had this accidental, very nice effect to transform a local Hamiltonian to another local Hamiltonian. But the states do not follow the same rule. What is local in the superconducting picture or in the Majorana picture can become non-local in the Eisen picture. And indeed that's what happened. We had localized Majorana modes again that were correspond to degenerate states. And then transforming the Eisen picture, there became this hugely non-local equal overlap over the whole chain, and both of them overlapped together. So as the both degenerate states in the Eisen picture overlap together, local fields coupled them and lifted the degeneracy as easy as that. Just a single side Zeeman field could lift with its own strength both degenerate states. But in the Majorana picture, they were exponentially localized at the end. Any local field anywhere in the whole chain will have an exponentially detrimental small effect. Nevertheless, the equivalence, exact equivalence between the two systems is that the spectra of both systems are the same. The eigenvalues of the energy are the same. But the eigenstates, because the eigenvalues don't care about the transformation, which is position dependent, but the states are position dependent, they do depend on that, and you have the transformation from one to the other. And this is also an interesting fact that the Majorana particles that now are quasi-particles, are eigenstates of the system, and these are the quasi-particles that we really would like to have, they become non-local things. We don't see them in the Eisen system. Okay? Even if we know they have the same spectrum, they're mathematically equivalent. Oh yeah, let's use them. Nice, I can make them in the lab even. But where are they? There are no quasi-particles there. So, even if we had this transformation between local and non-local systems, the environment had each one acts locally. So if I have a physical system made out of spins, it has a local Zeeman field environment as a perturbation. If I had a fermionic system with modes, fermionic modes, then the environment would act with Zeeman fields, chemical potentials, right? Local again. So these are two different physical systems. Now, mathematically, I can transform one to the other. Or if you like, as we want to do quantum simulations, I want to pick up a fermionic system. Now that's the name of the game that we'll be playing now. Okay? I'll pick up the fermionic system as my theoretical system. I want to simulate it. I'll transform it to a spin system of Ising Hamiltonians. And then I want to do the manipulations I care about for the fermionic system. I'll do it in the spin language. So if I want to simulate resilience against environment in the fermionic system, I have to transform the local environment, local error or perturbation in the fermionic system into a non-local error in the spin system, see how it changes my states, and then deduce a result about my Majorana system. Okay, that's what I'll be doing as a game, as we set the conditions. We'll do a simulation now. I want to understand a fermionic system. I have in my hands a spin system. I'll be playing that game. Okay, and whenever I see a state, okay, that is non-local. Oh, look at that! It's two Majoranas. Okay, it's like the matrix coming down and moving. Seeing people walking around. So we will be doing a translation. But there is another also additional advantage, is that the spin system is not resilient against local Zeeman perturbation, but it's resilient against some non-local ones, the ones that come from the Majorana description translated. What types of errors do we expect to find in the fermionic system? We could have flip errors, A1 dagger A2, just changing populations around your chain. You translate it as sigma 1 minus sigma 2 plus. Or you can have phase errors, A1 dagger A1, they translate as a sigma Z. It's the only two you could have, okay? More combinations at all. And both of them actually, if you see their action on the plus and the minus states, they do change the energy of your system. Okay, that's why. So if you add it as a small perturbation compared to the energy gap, it won't change the nature of your ground state. So you can be effectively detrimental. But if you add a sigma x in the spin system, that couples directly the plus state with the minus state without going through an excited state, and will give you a phase factor. It's like adding to the general state the Hamiltonian, boom, coupling them. It will accumulate a phase factor between them, it will dephase them. Interestingly, sigma x doesn't correspond to an error that can happen in the fermionic system, because it will be changing the number of fermions. So, and will change the parity of your states, and we're not allowing that. So we said that we have, okay, number of particles destroyed, but parity, other is even broad. So sigma x is not allowed there. Isn't that nice? Isn't that neat? I find that quite interesting, actually. When you simulate the fermionic system with a spin, you have to completely ignore sigma x errors, because they're not there in the fermionic system. Is any questions up to now? So we discussed about the Majorana system and the superconducting Hamiltonians, and how I can do encoding, and how well or not is protected against errors, and how I can simulate it with spins. Now I would like to talk a little bit more about Majorana fermions and discuss the properties, if nothing else. These are really easy to work with. You write an operator, you split it in two. It's like working with complex numbers, right? How painful can it be? But let's see, can I derive out of this simple description all the properties of Majoranas? Like, see them as onions, we have a special fusion rules, and see them as special braiding properties that are not a big apart. What does that mean? Let's see, just a couple of slides. Let's assume I have two chains. I do need two chains in order to bring their beauty out. I need 4 of Majoranas because I have preservation of number of parity. So I cannot change the population of 2 Majoranas from 0 to 1. I need 4 of them and change simultaneously the populations of their pairs from 0, 0 to 1, 1. So I need 4 Majoranas. And I can arrange my chains to have a T-junction. So I can move this from here to there, and I can bring this up to this position and bring the other one from here down. So I can do changes actually between these Majoranas, even if I'm talking about chains. So I use these so-called T-junctions. So I'll forget about the strings connecting them because I can move them as I like. Good enough freedom to move them around. Now what I can do is, I want first, I give you Majoranas, write them as fermions. That's what you know and know how to work with. So we can write them as fermions, combine them in this horizontal way, gamma 1 and gamma plus I gamma 2 give me A1. Gamma 3 plus I gamma 4 give me A2. But I'm equally free to combine them vertically. I can do gamma 1 plus I gamma 3 giving me B1. And the other vertical mode, B2, is gamma 2 plus I gamma 4. I can combine them also diagonally if I like, but I'll get something very similar. I don't need to. You can do it, it's fine, but I don't need to. Now, these fermionic operators, the B's and the A's, are not independent of this. They're written in terms of the same Majoranas. And indeed, if you try to calculate their commutation relation between A1 and B1, you find something strange. Half. I don't know what that means. Okay? It means nothing. It means that you're messing up with things that you shouldn't be. So let's look at now the Hilbert space of the A's. Can be populated, both of them populated or both of them empty. And the B's, they can be both populated or both empty. And see, can I transform, can I write the populated states of the A modes as states of the B mode? And yes, you can do it just by playing a little bit with the creation and equation operator. So let's pick up empty modes in the horizontal direction, in the A direction, both of them in the 0. And then I apply this operator to B1 diagonal B1, the B operators. And then I want to see, after applying this B operator, does it correspond to populated or empty state with respect to the A modes again? Alright? Second, I know the computation relation between A and B, I just calculated it up there. So you can compute this one and act it on the 0, 0, and you know how these operators act on those states. Just the eigenstates of these operators. You know how to act. So you can do them for the A1 diagonal A1, or for the A2 diagonal A2. And then you will find that actually for either whatever choice of population you use, you find exactly the same state back. Just commute, blah, 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 you have from 0, nothing happens. So this state, acting this B operator on 0, 0, is an eigenstate with eigenvalue 1 of the population A operator. So it has to be the 1, 1 state in the A base. This is an interesting relation. Let's look at this second relation because I know that then the B1 dagger B1 acting on 0, 0 is equal to 0, 0 in the A basis, that's 1, 1 in the A basis. But B1 dagger B1 acting on a state, giving you something non-zero, ooh, that's really telling you that this state has a population in the B. The B modes are populated. The were populated, it will be a 0. So the B1 dagger, B1 acting on the state is opposite here. This is the one, also similarly you'll find that B2 dagger, B2 also has the same properties, exactly. That liaison goes also for the B2, so they're exactly equal. So this is the 1-1 population in the B mode. The normalization here is just to keep the whole state, it's a projector for it, right? So, and just by using this relation here, you see that the 1-1 in the B mode is equal to equals proposition of the 0-0 and the 1-1 state. Okay, it's interesting. If you have the B modes populated, you can bring these Majoranas together, you can measure all the populated 1 and 1 state, you bring them apart, now you bring them like this, half of the time you'll find that they're populated, half of the time you'll find that they're empty, actually in a quantum superposition. It's strange. It's alright. We never said we'll preserve the number of particles, only their parity. Okay? That's important. Similarly, you can calculate that the 0-0 state is equal to the, in the B mode, is equal to the 0-0 minus the 1-1 in the A mode. So you can view these populations in the A modes and populations in the B modes as a change of basis. Same thing you do with polarization, measuring the vertical, horizontal, the circular polarization. You find the over 45, you find these things. It's just a different basis of measuring exactly the same thing. These two bases are related by Hadamard rotation. In the anionic picture, we call it the F matrix, the F mode. Okay? That's important. So this is the fusion properties of non-abelian anions. If you have time fast. Property means I have these sigmas, my Majoranas, sigma is a Majorana. I can combine them together and I can get either a vacuum or a fermion. So this is a vacuum or a fermion. Now this is a definite fermionic population, it's not a mode. So if I combine two Majoranas together, like the gammas, I call them gammas there, I can have an empty, either the 0-0 or the 1-1 populated fermion. So these states, in terms of Hilbert space, they tell you the fusion of Majoranas. That you get two possible outcomes out of a fusion. This step is called a fusion. You get two possible outcomes. It means that you have non-abelian atoms. The property of non-abelian or of statistics or of anions, the important property is their statistics. They're not known about the fusion properties in the popular culture as much as they're braided. What happens when I'm exchanging them? So let's go and see them. What happens if I braid? So what I'll braid is actually, I'll exchange the position of gamma 1 and gamma 3. I'll move gamma 3 up here, move gamma 1 down, and then gamma 3 in. So make a single exchange between the two of them. I have a Hilbert space of states 0, 0, and 1, 1, so either the A or the B, doesn't matter. So the exchange will be some unitary evolution acting on these states, on this Hilbert space. And I'll write down this unitary, and then expand it in terms of operators, of Majorana operators. It acts only on gamma 1 and gamma 3, so it can be written as a function of gamma 1 and gamma 3 only. But gamma 1 and gamma 3, they square to the identity, because they anti-commute with themselves, so their square is equal to 1, or half. Okay, so all the terms, the complete basis I can expand an operator U in terms of Majoranas involves either the identity, or gamma 1, or gamma 3, or the product. Anything else falls within these 4 terms. So I put some coefficients, some complex coefficients, A, B, C, and D. Just the complex numbers that I need to determine. Okay. Now I need to find out what this A, B, and C is. The conditions I can impose on U is that, first of all, it's a unitary operator. You diagonal U is equal to 1. And second, when it acts on the operators, on the Majorana operators, it transforms gamma 1 to gamma 3, and also gamma 3 into gamma 1. So if I to U gamma 1, U dagger, to get gamma 3. So something proportional, some phases probably, but I'm really change the position of these two pieces. So I have to, let's say, the other way around. So if you calculate these things, you do all the algebra, it's rather simple. And actually you need to impose one more condition. The extra condition is that we have, if you have 3 of them, gamma 1, gamma 2, gamma 3, and you break gamma 1 with gamma 3, and you break gamma 2 with gamma 1. When you fuse gamma 2 and gamma 3, you get a single fermion, and then you actually break this thing back into gamma 1. If you demand that this evolution that has a continuous stream that goes up and below, if that's identical, gamma 2, gamma 3 is going into an A. It's topologically it is because you can move this easily back and forth. So if you can find the evolution of this braiding, the evolution of this braiding, and equate them to the identity that nothing happened, which means that these 2 braidings equal to this braiding. So you need this extra additional condition in order to solve exactly for A, B, C, and D. You find 2 solutions. And a big one. So if I do 2 exchanges, I can write easier my state if I calculate this square. I find the phase factor to the I pi, or a gamma 1, gamma 3, which is the non-abelian. Okay. So I can write this gamma 1, gamma 3 in terms of the A operators, A1, A2, A1, A2 dagger, A1 dagger, A2, or A1 dagger, A2 dagger. Fantastic. I can start from both A modes being empty. I can braid these 2 onions together, and then both modes will become full, occupied. Isn't that fantastic? That's fantastic. Both of them simultaneously, parity has to be preserved, but you can move from empty modes to full. Or you can start with one mode being empty and one mode being full. You braid them, you never touch each other, and then the above will become empty and the other will become full. Alright? So the population would travel from one side to the other. I think I can demonstrate that with a piece of chalk. You have to really understand how strange this is. You have a fermionic mode which has is full, is occupied, occupation with the chalk, and another one here that is empty. Okay? Alright. Now, I'll braid one Majorana around the other one. And the population moves from this side to that side. Okay, I can't do the trick, I'm not a magician. But this is the same thing as they're moving from one side to the other. Right? So it's really a miraculous thing. If you have these superconducting wires, you'll be able to teleport the state from one side to the other without ever touching. Okay? Thank you for believing in me. Sorry. Indeed, and these 2 operators remove population from one side to the other in a unitary way. So why do we have a phase factor and evolution? I mean, these are non-abelian islands after all, right? Now, what does it correspond to? Well, it does correspond to the exchange of two Majoranas that live on the same chain. Still, you can exchange you have a single chain and move the Majoranas one around the other. Move them, exchange them. Then you ask the question, what happens to the state of the system? And indeed, we acquire only a phase factor. The population is not allowed to change. It has to stay the same. And there is an easy way how to simulate this with the spin, the Ising model. So that will be our quantum simulation by using adiabatic evolutions. So adiabatic evolutions means that I could encode the state in the ground state of a certain Hamiltonian, and then I want to move to another Hamiltonian, to another ground state, to another Hamiltonian. This transition could be moving two ions together, exchanging two ions. If I move very slowly the parameters that map one Hamiltonian to the other, so I introduce the parameter lambda that move me from a Hamiltonian H1 to a Hamiltonian H2. So for lambda equals 1, I have this Hamiltonian. For lambda equals 0, I have this H2 Hamiltonian. So if I move them slowly and make sure that the energy gap never becomes 0, I can transform from one Hamiltonian to the other, or from one ground state to the other ground state. And indeed, I can do that in this following way. Imagine I have a Majorana side here, a fermion mode here with two Majoranas, and another fermion mode with two Majoranas. They have a superconducting interaction. I transform that into the Ising picture. Is an X-X interaction, okay, between the two sides. But really what it means, this X-X interaction, is that these two Majoranas that decompose my sides, they are interacting. And I have two other Majoranas in A and B sitting at the endpoints. I would like to exchange them. And how you can exchange them is adiabatically turning on from X1 to the X2. That will move the A from here into that. And turning on the Hamiltonian H2. H2 is just a chemical potential. And in the language of speech, it's just a sigma Z operator acting here. And now I have this A and B Majoranas sitting next to each other. Exchanging them, or rotating them, correspond algorithmically, really, into applying the unitary sigma X operator. So this will exchange the two modes together, and then I can move from H2 into H1 by turning on adiabatically switching these to Hamiltonians, and in that way you change B to A. There are many other ways how you can do it. You can move one up, move it here, move it down. It's more complicated. That's the simplest and a little bit cheating into this unitary rotation here, but it really does the same thing. I'm not particularly concerned about to get the physics right, then you can extend it to bigger systems. And this will give you the phase factor. This gives you an I factor, and if you do it twice, you get a -1. Exactly what you expected by exchanging, by the analysis we did before. Yeah. Double exchange, a minus factor, single exchange, an I factor. And this has been easy.
Sorry, I don't get the magic. You started from that Hamiltonian, from the Hamiltonian of your superconducting Hamiltonian, and then from there you created your gamma 1, gamma 2, and gamma 3, gamma 4. It's not surprising to find your Hamiltonian there.
You find it.
I mean, you do this grading in Majorana thing, but in reality, if I think about the physical system and start from my two fermions on two sides, I decompose it mathematically into my Majorana fermions. And all I see at the end, if you do the grading, which is maybe something mathematical or whatever, all I see at the end is that I get back my original Hamiltonian.
Right, exactly.
So
absolutely, yes.
I don't get the magic there because I started with one Hamiltonian, it's no surprise I get the same Hamiltonian there.
Right, you get exactly the same state factor, but you can get the phase factors, you get a better phase out of it. So you start with the same Hamiltonian, you do some evolution, a cyclic evolution, you come exactly to the same Hamiltonian, but the states evolved in a non-trivial way. And actually get the Berry phase of these evolutions will give you a Berry phase of -1. And this Berry phase is topological, it's not, can be deformed, this is exact.
What still I am confused with is we needed to start from, you start from some, let me call them real fermions. I like my picture that it's like something I can measure, I'm sure I can measure at least in the lab. And then you say that you get this Majorana fermions, okay, I understand the composition. But then, for example, you said that you can recombine them in different ways, write them or whatever. Who allows you for that? I mean, it's, for example, doing the recomposition of your Majoranas in different way, like your I and your B. Why can you do that? I mean, apart from saying it's mathematical. Mathematically, I can do what I want, but physically, I start from my firm.
So here I'm manipulating spins. So I encoded, so here I'm talking only in the spin language. So I translated what means to have Majorana fermions in a superconducting system into a spin language. So I'm measuring spins, everything has a good, so if I measure plus, oh, I know I have a Majorana state populated or minus, I know what it means. So that's really, it's as simple as playing with qubits and so on. In terms of fermions, if I actually had a superconducting system and I wanted to make these measurements, you can make a joint measurement of two endpoint Majoranas by having an EPR state, actually. So it's possible to use non-local entangled states in order to measure the populations, the non-local populations, so the quantum information inspired, let's say, with the right language, if you ask me to see these objects, that you can measure these populations and the parity of the populations. Another way, maybe more physical if you would like to see it, is to bring the endpoints near each other. So make the chain smaller. If it's solitonically trapped, move them near each other. And now, if you keep on tracking the energies of your system, if the energy stays exactly the same, it means now you have the vacuum, the population is a vacuum, or if these two guys are populated by a fermion, then bringing them together will take the zero energy into the first excited, which is the fermionic state. So you create that will be the most physical, let's say, condensed matter way how to view it. So here is the separation X of two Majoranas, gamma 1 and gamma 2. And here's the energy. And here is your superconducting gap delta. These Majoranas have energy 0 when they are far away from each other, they're degenerate. Now, you keep track what happens when you bring them next to each other. Do they remain 0, or actually the energy goes up? So, if it's populated, if you're in the psi state, one has psi here, right? So if I bring them near each other, the vacuum state, you know, this one will go, the energy won't change, but the populated will jump up. Actually, it jumps up in a very funny way in 2 dimensions, because, yeah, but in 1 dimension it will just go like this. That's the measurement you can do. If you can resolve spectrally your system, for example. Yes, please. Thank you. Yes. Near the end, thank you. So that's the phase, the abelian phase by changing the endpoints of two Majoranas of the chain. In order to do a non-abelian phase, you need 2 chains. Here I have a small comic sketch how to do it. So I have one fermion, another fermion, both coupled superconductively or XX. And I have another chain down here. independent, it's not coupled with the previous one. Again, the same, it's a little bit bigger. And I have a simple fermionic mode sitting in the middle. That will be my bus, my T-junction. Initially it's decoupled, but I have it there in order to be able to hop on the island and leapfrog, you know. So I will move from 1, 2, 3, 4, 5. All right. So from 1. So all the Hamiltonians I need now is just XX, so translated in the spin language. I need either XX or Z, local fields. Right? So XX is between this, XX here, and XX here. This chemical potential Z. That's that. And the black dots again are Majoranas, right? Decomposition of verbs. So I want to move A into the place of C. So I'll move from, first of all, A from here to there. Just by adiabatically changing from the XX and the Z to the XX here and the XX there. Switch off this Z interaction. And again, the same thing for moving in, and then also I move this C from here to there. Okay? So basically I switch off the XX and I switch on the sigma Z here. And then I move this A from here to there by switching off the Z and introducing the XX there. And again, I continue. I want to bring this C all the way up here. I do the steps and I have everything well defined, just moving adiabatically, going from one to the other, turning on one, turning off the other. There are no any energy gaps closing. Everything happens in a nice way. So you change this to, and then if you measure, the states of your system, indeed you change the populations. Okay? If you do it twice, you go from both of them being populated to both of them being empty. If you start from rising states plus, you go to the minus. It's nice. Do it with mathematics. Yeah, big on hand, a little more fun. And that's that. That's how you can demonstrate with a spin system Majorana physics. You have to be careful. You're doing a simulation, okay? Local states in the superconducting system became non-local in the spin language. That's all right. You do a simulation, okay? Still, you're manipulating locally your Hamiltonian, which is really fascinating. You're braiding things. Things haven't been braided in the laboratory with Majoranas yet. We claim we've seen them, but until you do the braiding, the issue is not won't be settled. Okay, you need to braid. This is, let's say, an in-between step. You do a quantum simulation. You build the necessary control in order to do it with a complete fermionic system. You do it with a spin system. You can find different media to do it. Okay, photons or atoms or atoms. So you can use it for encoding information. Even the Ising Hamiltonian is interesting for encoding. It's been demonstrated with ion traps and so on, I believe, recently. Or you can do it for fundamental reasons, just to demonstrate the abelian and non-abelian properties of the Majorana fermions. Please do find your favorite medium in order to simulate them. All right, so thank you.
Thank you very much.
My question may be just about your last phrase, about favorite medium. If I'll take just simple two-level system like in the atom, background state and excited energy state, can I do something similar with a number of such two-level systems, or it's impossible because if I have localized electronic states? Or what I have to do in order to make this delocalized states, to couple these atoms with the light, something like that. What is your opinion?
The important ingredient for this quantum simulation is to have an Ising interaction, sigma x, sigma z, sigma z. So I will need two subsystems as a building block that have this Ising type of interaction. So, I mean, I can encode everything within that big Hilbert space and do this manipulation. So you have n or 2 to the n levels of an atom, and then.
Is it like a flip-flop transition? One goes
Yes,
down.
absolutely.
So it's possible to do it with in optics with atoms.
Two atoms, they're excited, and I bring them nearby, and I have an energy shift. That's like a ZZ interaction. So I can use that one. So different media will have different ways how to do it, and indeed, that is, I believe, it can be done with photons. Just you can do quantum simulation of a Hamiltonian with photons and some projections and so on.
One question? Yeah. To what purpose can anions be used?
Anions, in particular Majoranas, you can encode information, and I demonstrated a little bit the resilience against local perturbations. So that there won't be affected. If you encode the qubit in Majorana fermions, it won't be affected by local perturbations. So you can now use this encoded information. Okay, indeed, yes, as you have mentioned, I could use the anionic statistics, the braiding, in order to manipulate that encoded information. Okay, so we can go from one basis 0 to the populated base 1 just by braiding them, and this is pretty amazing. We do it's like adiabatic quantum computation, where you move from one state to another without bridging the gap at any point. And also, all the manipulations of the Hamiltonian are local. Just move one anion with local phrases around the other. So it's a very well-controlled way how to build gates, which are really adiabatic quantum computation. And also, there are topological errors in the performance of the gate won't affect So there are certain advantages, like the independence of the exact shape of the path of the adiabatic evolution is an anionic characteristic of this topological phrases you get. You can do it adiabatically, but then errors might be affecting the system.
Okay. Last question.
So, my question is, so is superconducting model easy? Okay, so let's say, so it's a condensate again of these anions, like so does the gap itself become more robust to, let's say, local perturbations? Because I have a condensate of these parts. Not, so everything is placed by that.
That's right, yes. So the question is indeed, can I infer back? As we said, we can encode information in a robust way, but can I go back to the quantum phase of my system? Does it become more robust as a promise at the very beginning? And indeed, that's a result you can deduce, that the superconducting phase is robust against the errors we introduced. Yes.
So if the local perturbations are like of the order of the gap,
then you lose it. No, it has to be small.
Okay. So,
but what you don't lose is that if I couple something else on the end state, if I have another fermion and I put it on the end state, okay, then the characteristic of two Majoranas at the end won't change. And this is really the amazing thing. Okay, you have two Majoranas at the end. Anything local, you put fermions in there, it won't destroy the property that you have with the Majorana here and another Majorana here. It's a fermion that is delocalized. The only way you can destroy them is having another delocalized fermion and then attack them, or have two chains combined. But the environment cannot destroy two Majoranas moving around. So you have to go to much higher orders in interactions in order to destroy this property. So the topological property is robust against attacks at the end.
Okay, so let's end the again.
Thank you.